we are continuing with the Saint-Venant equations. So now we are moving to the realm of dynamic open channel fluid flow simulations. We start off with the continuity equation and the equation of motion. Okay, so this is something that's well known. Okay, and also the momentum equation should be familiar. The only difference is that now I've replaced the source terms with the open channel source terms. Now, if the density is constant, and this is going to be interesting because so far we usually said that the pipe area is constant, so we factored out, we could simplify with it, and density was varying, or the density was rewritten as a pressure for slightly compressible flows. Now we will say that the density is constant, but the area is changing because this is here the wetted area. So if you consider this case, so you say that the density is constant, then the continuity equation is reduced to this equation, which tells you that how the wetted area changes and the flow rate changes. And very similar things happen with the equation of motion. So you have A times V is Q, and then A times V squared is A squared V squared divided by A, so you can rewrite this term in terms of flow and flow rate and area. And then you have the right hand side. I'll have to change this again. I will do it in the lecture notes. Okay. Now, we have to be a little bit careful about how to replace this pressure. So naively, you could say that this pressure is the hydrostatic pressure, but it's not that easy. What they do very often is they say that this pressure here, because this is essentially the force due to the pressure across the surface, across a section of your channel. So what you want to do, you want to compute the average pressure, okay? And the average pressure is simply the overall pressure force divided by the area, the cross-section wetted area. And this can be computed by integrating the pressure distribution along the channel width, okay? Which will give you this quantity, where this I1 is the value, the result of this integral minus these terms, okay, because these are factored out. Now, of course, if you have a simple rectangular channel with B being constant, the average pressure is nothing else but the half of the hydrostatic pressure, because this is your pressure distribution. So this is 0, this is the water height, okay, and then the average pressure is, and this here is rho gy. Okay, so this is the case when you have a rectangular channel and B is constant, but you'll get different results. For instance, if you have a circular pipe, if this is your situation, okay, because then the channel width, so this function will vary as you vary the water depth. Anyways, now our dynamic equations can be written as this, and these are the so-called Saint-Venant equations. Okay, very often used by civil engineers. Now what we should see is that this set of equation is again something like this. Okay, so again, the temporal derivative of something plus the fluxes equal source terms. And if you rewrite it again as a quasi-linear set of partial differential equations, you will get this coefficient matrix A, and for this coefficient matrix you will end up with this again if you assume that you have a rectangular channel, okay? And then again you compute the eigenvalues of this matrix and you'll get these eigenvalues, out of which we see that the wave celerity in a rectangular channel is the square root of g times y, okay? So I'm not giving you here the details of the calculations, it's rather straightforward, okay? You see here that you have q squared over a squared, this is v squared. Then if you plug the previous equations for a rectangular channel, then this term turns into g times y, and then q over a is again the v velocity, and then you do a standard eigenvalue analysis. So what we see at the moment, that the open channel dynamic equations can be written in this form, okay, and this form teaches us that the wave celerity is c g times y square root. Okay, so later when we are going to deal with the Lax-Van-Drove scheme, we'll come back to this equation, but now let's see the same problem as a characteristic equations, okay? So again, I'm not giving here the details of the computation, but it's a rather straightforward calculation that for a rectangular channel of constant width b, the Saint-Venant equations can be rewritten in a differential form like this. And then what you do is that you replace the water depth. This is a crucial step. You replace the water depth by wave celerity. Okay, so whenever you see the temporal or spatial derivative of y, you gotta write the temporal spatial derivative of this thing, which is 2c ct over g. Okay, and then of course you plug this back into the differential form, and then you add and subtract these two equations, and you end up with the characteristic equations. Okay, so again we see that the slope of the characteristic curves are v plus c, v minus c, just as in the case of open channel flow, but now the Riemann invariants are v plus or minus 2c. Again, c being the wave celerity, which is directly linked to the water depth. So this seems pretty straightforward, and I also listed here a couple of equations between gas dynamics and open surface flow, okay, just for your convenience. And then let's see how we build a numerical technique on this. Now we have to be careful, and there are important differences from the slightly compressible case. So first of all, the wave celerity now is not constant. As depth varies, so does the wave celerity. And secondly, the flow velocity can easily increase beyond the wave celerity. So for instance, if you take 1 meter of water depth, then the wave celerity is 3 meters per second. So this is not too high. In the case of open surface flows, it can very easily happen that you have a supercritical flow, meaning that the flow velocity is larger than the wave celerity. And then we have to be careful. So this means that all our characteristic lines are changing, the slopes are changing, both the C plus and the C minus lines. So first of all, we have to be careful with the time step. The time step must be chosen in such a way that neither of these characteristic lines, so for instance this one, goes beyond a grid point. So for instance, this time step is too large, because if you start a characteristic line from, let's say from this grid point, then within this time step it will pass through 2 grid points, which is not good. So what we do is we limit the time step by this formula, which is also called the Courant-Friedrich-Levy stability criteria. This is a very, very well-known time step criteria. Okay, and then when we are trying to update the points, what we need to do, we need to find those left and right points which have the following property. If I interpolate velocity and the wave celerity from the grid points to this left point and compute the slope, it will hit exactly the next grid point. Okay, so here are the formulae how you do that. This is for the right point here. This is for the left point. Okay, so I wrote here down all the equations. Please have a look at it, think it through. So basically you have a linear interpolation between the node points. Okay, there is some discrepancy with the eyes. So the spatial grid is always denoted by J. This is a typo here. Okay, I will also correct this. But it's rather straightforward. And then you work out all these equations, and then you proceed as usually. So once you have the left and right point, you compute alpha and beta, and then you update your Riemann invariants. Finally, I wrote here down another technique which I think is even more simple for computing the left and right points. Please also read this carefully, okay? And I've also added an implementation in MATLAB for this. So this is the crucial part, how you interpolate these points. I would like to ask you to carefully read it, make yourself notes, and try to understand what I'm doing here. It's not rocket science, but it definitely needs some effort. Okay. So here I've added another case, open channel unsteady. This is another MATLAB simulation. You can run it, and you will see, because the parameters were chosen in such a way that you will see that this characteristic lines-based solver is absolutely happy with having hydraulic jumps. So here is the code itself, and I will start running it. Okay, so what you see on the upper side, you have the water depth. On the lower, you have the velocity and the wave celerity. Wave celerity is the red one. So whenever the velocity is higher than the wave celerity, then you have supercritical flow. And I've added a bump here, which is a well-known test case for hydraulic jumps. And what you see here is that you start off with a subcritical flow. Okay, so velocity is smaller than the wave celerity. And then after the bump, you have a hydraulic jump. So temporarily, the flow velocity goes beyond the wave celerity, and then through the hydraulic jump, it slows back to subcritical. And have a look that this technique is absolutely happy with computing such problems. It doesn't even need a special handling. And have a look at this gradient, how large this is, and yet no oscillations are present. Okay, so this is a very, very nice feature of this technique. Okay, so that was the second part. And then in the next video, which I will do next week, I will add the boundary conditions, okay? How you handle boundary conditions in the case of open surface channel flow. Bye-bye.